All right, welcome back. We are GAME3001, that's Artificial Intelligence, in the winter 2021 semester at George Brown, and it's week 12, but less than 11. Part one of our broadcast, and in this part, we're going to be talking about goal-oriented behavior, which should be spelled with a U because we're in Canada, and rule-based systems. All right, so what those things are. And remember, we talked about this whole second half. It's all about decision making. So let's talk about that. Where are we? Well, this week we have Lab 9, which is going to be due Sunday. I'm going to release that in about an hour or two. We also have, just to remind you, assignment 4 now. We're past assignment 3. Assignment 3 has been completed at this point. And assignment 4 is going to be due Sunday, April 18th at midnight. So that's the very last day of semester at midnight. That's when that thing is due. So hopefully you've had a good chance to work with assignment 3. And before we move on to talk about anything else, any questions or how was your feeling about assignment 3? Can anyone give me any kind of feedback? How do you feel you did in terms of an understanding on assignment 3? Assignment 3 is the hardest one you've done so far, right? And assignment 4 is going to be that much harder. So what is your feeling about assignment 3? Does anyone have any thoughts they want to share? You don't have to speak up. You can just share it on chat. It was a challenge. Yeah, I think so too, Miguel, for sure. It's definitely a challenge because a couple of things, right? One of them was a lot of details, right? So lots of little things that I need you guys to do this time around. It wasn't just a little demo. This is a prep for something that's greater. Okay, so that's why assignment 3 was more challenging as well. Anyone else have any other comments they'd like to add about assignment 3? How they felt about it? Even the people online on YouTube, you can also comment if you're interested in giving your feedback. Catherine says, challenging, but I enjoyed it. Very satisfied when things worked how I wanted. Yeah, and I think that's the beautiful thing about programming, right? We see immediate results when things are working well. Bad thing is sometimes we don't see immediate results. We see immediate errors, but it's good when it's working and you've planned it the way it's supposed to be. You've got the underlying, or let's call it the underpinnings of a good AI system, which is what you're really trying to create here in this course. After this course, remember, once you've done assignment 3 and 4, you'll have the basics for what you need to create something a little bit more robust in your own game engine, if that's where you want to go. Or you have the idea of how things should work. So when you work on somebody else's game engine, or even a commercial game engine like Unity or Unreal, you'll have an idea of how all that stuff works. Okay, so that's the idea behind it. So assignment 4 is going to play upon assignment 3 like we talked about before. So it's going to build on everything that we talked about in assignment 3. So make sure, everybody, that when you're doing assignment 4, that your assignment 3 is functioning. If your assignment 3 is not functioning, you're going to have a problem. Sophia also on YouTube commented, really fun, but yes, definitely challenging, especially working with obstacles. Yeah, that's always interesting. How you do line of sight with obstacles and all that kind of stuff. The idea of path nodes and all that kind of stuff is very challenging as well. So totally different than maybe what you've done before. All right, so that is assignment 3. We're moving into assignment 4 now, and we're sitting at week 12. So it's the week of March 30th, right? So last week of March, actually, as we're moving into April month. We're going to be talking about goal-oriented behavior. A couple of changes. One thing that I want to point out is special topics, machine learning for games, and all that kind of stuff. I'm going to move one more week forward. So I'm just going to put this forward for you guys so you can see it. I'm going to move the special topics topic, so machine learning for games and stuff. I'm going to move it to this week. Okay, so this is kind of where I want to put it. And the reason why I want to do that is because I wanted to move utility AI over to this week. So I'm kind of moving utility AI over to next week as well. I want to take some more time with it, the concepts behind it. So utility AI is moving to next week. That's where it's going to go. And then special topics for games and all that stuff. Not sure why I got these weird colors, but let's make it so that it's something recognizable. Like maybe this green color. with maybe an arrow at the other end. Sorry, fool around with this kind of stuff later. Anyways, but you get the point, right? That next week we're moving stuff from utility AI is going to move to next week, and then machine learning, reinforcement learning is moving from next week to the week after. So the final week of semester, all right, pretty much. So that's when everything is moving. Again, keep in mind that as we move into week 14, that it'll be the final teaching week will be in here. I think it's an interesting topic, machine learning for games. And that's why it's going to be something that we're going to move over here. Okay, so that is how we're structuring stuff. Just wanted to give you an update on that, what's happening. And now we're going to move over to what is goal-oriented behavior. So let's talk about this a little bit. So up until now, what we've talked about is how we make decisions with AI. So if I want to move right or move left, there needs to be a reason why. If I'm going to search out the player, I have something called a sensing suite that we've created, right? We've got a line of sight or field of view for the autonomous agent AI. It's got a field of view, and on top of the field of view, a lot of times what they also have is some kind of sensing radius that we've talked about before. Okay, so those are two things for us that makes up the sensing suite, somehow of being able to detect the player. There are other ways of detecting the player as well. As an example, being alarmed. So getting an alarm status from another agent, is another way of getting detected. So they're not in your radius and they're not in your field of view, but you've heard an alarm condition. So that way you better do the next step. Part of your decision tree or your behavior tree is, hey, if I've got an alarm condition, but I don't detect the player in any other ways, then maybe I need to go downstairs, or maybe I need to go up on the tower to see if I can see the player. I've got an alarm condition. So that's a third way of really detecting the player. We don't have that in our game because our game is very simple, right? But yes, there's other ways of creating some kind of, or adding to your sensing suite, okay, than just two ways. So that's the other thing. So some kind of alarm. You tripped an alarm, you made a noise, that kind of stuff, or you got seen. One of those three things. If your player is playing and your AI is looking for you, that's the way to getting that done. And the alarm can be tripped in that you broke open a door, you open up a chest or some kind of thing, you picked up loot that you're not supposed to. An animal made a noise, so you didn't make a noise, but some animal saw you, or you're fighting something. You're making noise, and the noise itself, depending on the intensity of the noise, could detract other people that are trolling. So that's very interesting the way that would work. All right, so lots of ways of doing stuff. In our case, we're keeping our sensing suite really simple. So one of the things we haven't done yet is kind of said, well, why is the AI doing stuff that they're doing? So we've done the how, right? Like, this is how we're going to do stuff. We're going to make a decision and do A or versus B, as an example. We're going to go here or do that. We're going to attack or defend. We're going to, depending on an if condition, this is what I'm going to do. This is the action that I'm going to take based on the condition that is present, right, in the game. But the question is, why are you doing it? Okay, why is the AI doing it? What's the intent of the AI? So the idea that the AI has its own desires and goals, right? And again, one thing to notice is just a set of inputs that results in some kind of action, okay? We can make an AI seem like it has goals, and we can do that by giving it the ability to hunt down the character, as an example. Or maybe we want it to have a desire to live. So we can make it react to low health and that kind of stuff. We've kind of done that in your assignment 4, where the AI will flee if it's got low health. But the desire to live can do other things too. Like, for example, it can be afraid of danger, any kind of danger condition. If it detects, other things, as an example. So things like, I'm really scared, right? I heard a noise, and the player is more powerful than I am. I'm going to run away because I've got some self-preservation in place. So techniques like this, like where they have goals, are some simulation games like The Sims. You might see some, things that they would do. There's other simulations games out there as well. Most of the simple goal-oriented behavior that we see out there is seek and destroy the player. That's something that we see a lot. So when we have people simulation games like The Sims, right? They might be wanting to eat when they're hungry, sleep when they're tired, chat when friends when they're lonely, a bunch of different things. And it makes these characters seem like they're human. Could we use a decision tree for those things? We could, but then we'd have hundreds of actions to choose from because one action would lead into an array of other actions. So that would be a challenge. And one better approach might be to present a character with a bunch of possible actions to choose from, and we have to give them the one that meets their immediate needs. Okay, and we call this goal-oriented behavior. All right, so they might have an immediate need or desire, and they're going to fulfill that desire. So again, we just talked about it. Goal-oriented behavior takes into account goals or desires, something that they want. Okay, there is, again, there's different ways. We also have rule-based. We can make them follow certain rules. And again, what it says is it's still fairly rare in games, and I agree with this because having true goal-oriented behavior for AI, it creates a very robust and sometimes challenging environment to kind of live within. Your player to live in an environment that has autonomous agents that have their own goals and motivations. So when we think about goals, AI may have one or more of these, and a lot of times we call them motives. What is their motive, right? Again, we could have a lot of these. Several could be active at once. That's something that's new that we didn't have before. Normally we have like one state. I'm in patrol state. I'm in, attack state. I'm in defend state, as an example. But we could have a bunch of them, motives or goals, if you will. I want to eat because if I don't eat, then I will be weak. I want to regenerate my health. If I've lost health, I want to kill the enemy. These are a few of them that can act all at the same time, right? Each goal has a level of importance. Okay, so let's think about this as a weighting, if you will. And this weight is called insistence. So how insistent is this goal? How important is it? A high insistence will influence the AI more strongly than a lower insistence. So example would be, if I'm really hungry, then that would be a higher insistence motive compared to I haven't lost any health. So therefore, that would be a very low insistence motive. We're going to talk about these things more often. Next week, when we talk a little bit about utility theory, it builds on goal-oriented behavior. Okay, that's what it does. Okay, so let's talk a little bit more about this. So again, think about this, that the AI will try to fulfill each of its goals so that it can reduce its insistence. So I have a insistence that's really, really high, right? Let's say I need to eat, I need to breathe, I need to drink, these kind of things. And for survival type games, if you want to make a survival simulation, right, then the AI will try and maintain some of these things. For example, I need to be able to breathe. If I can't breathe, then I will die. And if there's a self-preservation motive, then that might be a very high insistence goal. A good example of that is I'm underwater. If I'm underwater and I've stopped breathing and I'm losing my oxygen, as an example, if I get low enough, I'm going to try and breathe, which means maybe means break to the surface, if I'm underwater, as an example. Or maybe, as an example, I won't even go into the water because I don't have an apparatus that helps me breathe. It's too dangerous, as an example. So these are things that we want to do. We want to try and reduce the insistence. And some goals can be completely eliminated, all right, if we really want to. Some goals also some games also might have a fixed set of goals that persist. Again, simulation games is a good example of that. one thing that is challenging is goals that don't have an insistent value. All right. So, that is a challenge. So we always want to have some kind of value or data that we want to actually allow or to kind of tack onto a goal. So if I have a motive, there's got to be some kind of level or some kind of data that gives us an idea of how insistent that is. Okay. I could also call it levels of hunger. I have 3 levels of hunger, 5 levels of hunger, 10 levels of hunger, whatever it's going to be, right? And the higher the levels of hunger are, maybe if I have a werewolf kind of autonomous agent, maybe it'll transform into a werewolf and go eat people. I don't know. Then there's going to be something called actions. Okay, we've already talked about what actions are from a decision-making perspective. We have a condition, right? We usually have some kind of transition state for using state machines, or maybe there's no transition. It just goes from one action to another, and we're pushed from one act to go from one action to the other with a set of conditions that kind of transition us from one state to another state. Okay, whether we're using a decision tree, a behavior tree, or if we're using a state machine, it's all the same. We have some kind of condition, and that condition is going to be either met or not met. And if it's met, we go and do one thing. If it's not met, we do something else. If then, else. Okay, but actions can be generated by the AI or objects in the world. And these actions, as an example, are aligned a lot of times with their goals, right? So example, cook food. I can't cook food unless I have a condition that is met in order for me to make that happen. I might have, for example, in a behavior tree, as an example, I might say, I need to cook food. Why do I need to cook food? Because I'm hungry. Hunger would be the desire or motive, right, to fulfill. I might have an insistence value for hunger. Let's say my hunger is level out of a 1 to 10. It's level 7. I have level 7 hunger. As an example, I've gone beyond, I don't want to go to, maybe it's critical at this point. So 7 or 8 might be critical. Okay, now I need to cook food. Well, I can't cook food unless I'm carrying food. So if I don't have food, then what do I need to do? Forage for food, right? I need to forage for food. Okay, go find food. I found food. Now my hunger is a level 8. Okay, now I need to eat. So I need to, well, there's 2 things. I can eat uncooked food, and that could cause me to be sick, right? Or, I could take a risk and cook the food, but, take a level of damage from my hunger, right? Let's just say, which one is, you can make a decision based on, the way you want to make some rules for the AI, right? And if I want to cook food is a contingent or dependent on the condition that I'm carrying food. Okay. So here's actions that will fulfill different goals as shown below. So example B, I have a goal, which is eat. My insistence is 4. I have a goal, which is sleep. My insistence is 3. Okay. Action, get raw food, right? So eat, my insistence goes down to 3, right? Action, get snack, my eat goes down to 2, right? Action, sleep in bed, as an example, because my sleep goes to 4. Sleep on sofa, you can see that the insistence. So goals could be checked against, as an example, other state attributes like time of day, that kind of stuff to make sure that they work, right? So, and what does it look like when it comes to choosing an action? I have some kind of goal, right? So here's the pseudocode for that. For every goal in goals, if the goal value, so the insistence, is greater than the top goal value, then now the top goal is equal to the new goal, whatever that goal is. So if somehow my insistence is higher than the insistence of my current goal, I switch goals. And with my switching goals, I take different kinds of actions. Okay? We're going to talk about utility next week in more detail, but this is kind of the pseudocode for how it works. Okay, it's choosing an action, and we'll continue talking about other stuff. All right, here's the next part, discontentment. Let's talk about discontentment. Discontentment is, think about this idea, right? I have goal to eat. And my goal to eat has an insistence rating of 4, right? My goal to go to the bathroom, right, has an insistence rating of 3. Action. If I drink a soda, I satisfy my requirement to eat, so it goes down to an insistence of 2. But I'm going to make it so that I add 3 to my bathroom, which goes up to an insistence of 6. If I visit the bathroom, my bathroom removes 4 from my insistence, so it goes down if I visit the bathroom. But this visit in the bathroom could have other side effects. All right, so one thing could affect something else. So 2 goals could play against each other. A good example, again, is that thing. I want to forage for food, right? Because I need to eat. So I forage for food. Right, but when I forage for food, I get hungrier, right? As I forage for food, right? Okay, good. So now, but I've got food. If I've got food, then cook it. I get hungrier, right? Because as I'm cooking. And then when I eat, let's say, depending on the food that I collected, it can reduce the hunger some amount, right? But not all of it, maybe, depending on how hungry I let myself get. So this idea of discontentment, right, is something that we want to try and reduce. I want to try and reduce overall discontentment, right? Because the more discontent I am in general, right, I want to bring it down. And discontentment is kind of an accumulation of all the goals that are pending. So all the motives, if I add them all together, it can give me a level of discontentment. Or you can do it in other ways as well. So how do we do that? Well, let's think about this. If I have my goal to eat, which is 4, and my goal to go to the bathroom, which starts off at 3, I drink a soda, my eat goes down, but my bathroom goes up. Okay, so now we might have a discontentment score of 29, right? Because maybe my bathroom, because it went up, and my goal here went down, as an example, my eating goal went down. Maybe we have some kind of weighting for each of these things, bathroom versus eating, and it creates some kind of discontentment score, okay? Again, there could be rules around this, right? And let's suppose that I go to the bathroom and I reduce my bathroom by 4 points to 1, right? As an example, then maybe what's going to happen is after I visit the bathroom, my eating, I'm not sure why it says 0. It shouldn't be 0. It should be like 1. But my eating goes to 4, let's say, as an example. It goes up again. I'm hungry again. Well, my bathroom goes down, and my discontentment as a result goes down because these are lower values. And maybe my eating is not as it drives my discontentment differently than bathroom requirements, okay? So Neil's asking, you're going with the current value. Yeah, it's kind of like that. I want to go with the one thing that's going to drive me the most, but also I want to reduce my discontentment score. So typically, if I have 2 goals that are competing, right, what is driving my discontentment score for more, right? Is it the higher level goal? Does each of these, or the higher desire from a weighting perspective, right? Is that the reason why I want to do it? So each of these things plays a role in the behavior that your AI is going to take based on the rules that you set out. Something that causes discontentment and so on, and the beginning score values. Okay. All right. So again, here's some pseudocode to start us off. We have some kind of action we're going to take. We're going to get this first action from a set of actions we're going to take. We're going to calculate the discontentment based on the first action that we've got, and against all of the goals, right? So goals are multiple goals. Calculate discontentment is a method that we're going to use. For every action in actions, this value, whatever the value is equal to the, I'm going to calculate discontentment based on the current action and the goals. As an example, now remember that the current action is, I've got the best value so far. Best value meaning I have the number that I want to do the most, maximized utility, if you will. We're going to talk about utility again next week. If this value, the current value, is less than the best value, then the best value is equal to this value. In other words, we're maximizing here. So I'm looking for the maximum value that's going to reduce my discontentment. And then I'm going to take my best action is equal to this action here, whatever the current action is. Okay. And then I'm going to return that best action out of my choose action method, right? When it comes to calculating discontentment, I'm going to take an action and I'm going to have a series of goals, right? As an example, we start off with my discontentment as 0, right? And then I say something like this: for every goal in the action, I might have several goals in a particular action, right? Calculate the new value after the action is completed, right? So, you know, as an example, my new value might be my goal value plus my action, and I want to be able to change my goal. When I change my goal from one thing to the other, what is the new value of that, taking that action with respect to that goal? All right. And once we've got that, then we want to add to the discontentment whatever the current goal discontentment value is, right? So that way it'll increase the discontentment potentially, or decrease it if it has a negative value. And that's how it kind of works. So kind of increasing or decreasing discontentment values. All right, here's something else we should also think about when it comes to goal-oriented behavior, and that's timing. So sometimes what we also need to know is how long a behavior will take. And if the AI knows how long it's going to take to do it, they may decide to do other actions, as an example, you know, to reduce this discontentment first, almost like the idea of low-hanging fruit, okay? So, you know, if something takes, you know, 30 seconds to do, and it's going to, you know, increase or decrease my discontentment, I can do it quickly to a certain level, then that's good, I'll do it. And the other thing is how often things change. So example, goal eat. It changes +4 every hour. So every hour in game time, let's say whatever game time is, right, my goal to eat will increase by 4, right, which will change my behavior, right? It's something that happens automatically. My goal to go to the bathroom will change +2 every hour, right? Starts at 3, goes up by 2 every hour. Action. Okay, so here's my 2 goals. Eat snack. Eat, well, it will reduce my eating discontentment by -2, and it'll take 15 minutes to do. Okay, interesting. After I eat, right, then because we spent 15 minutes and every hour things happen, we've just gone quarter of an hour. Well, because of that, eat went down to 2, right? Bathroom went up, right, because we spent a quarter of an hour, and bathroom changes at 2 points per hour. And we've done a quarter of an hour, which means it's going to go up by half a point, right, to 3.5. And let's say the discontentment values can be more based on these 2 values here to 16.25. All right. Action. Eat main meal, right? It takes an hour to eat a main meal. Maybe it's including things like how long is it going to take to cook it and so on, right? It takes an hour. I reduce my my requirement to eat by 4. Maybe eating becomes 0 afterward, but my bathroom goes up by 5 because, or to 5 because I spent an additional hour, and each hour it goes up by 2. So let's say, for example, it was something else and went up, and you can see that each thing changes as we go on, right? But even if I was to go with a, you know, sometimes depending on how long it takes, it could increase one thing and decrease another thing. So it can, we want to reduce as much as we can our level of discontentment. That's the idea behind it. Again, these are just some examples. And we could, there's some more pseudocode for calculating discontentment. All right, something called, there's something else called Smelly goal-oriented behavior. All right, so Smelly. Each motive or action, in this case, when we talk about Smelly, that a character can have is represented by a sort of smell. And the smell leads to the motive and could be represented several ways. And one of these is some kind of attribute on a waypoint representing the different motive sources. like a road sign, okay? We'll need to check the complexity or the distance of the path to each of the sources, and we want to choose the most convenient option. When I say the most convenient, it's gonna decrease the discontentment the most in the easiest amount of effort or time, right? So if something takes a lot of effort or takes a lot of time, maybe time and effort are related, then that's going to be less convenient than something that is quick. I can get rid of it, and it's going to reduce my discontentment really quick. Okay. Again, we can say that each unique path could have some kind of intensity based on the convenience of getting there. So, you know, a hearty meal could have a large intensity. A snack could have less intensity. Why? Intensity could also be, think about this as something that's useful, right? As an example, a long path to a hearty meal. So those two pieces, long path and hearty meal, might still be fulfilling that a medium path, more fulfilling than a medium path to a snack. So where a long path is got a very low intensity, it's not really a great thing to do because it's a long path, which means chances are your motives might change. Your discontentment might go up as you're traveling along that path. But at the end of the day, that your reward is going to be positive for the AI because they're going to be rewarded with a heartier meal than picking up a snack that is a medium path. That is not as great. Okay. So, so questions around this so far. So before we move into rule-based systems, because that is all what goal-oriented behavior at a very high level is about. We create motives, okay, for the AI. And those motives, right, have some kind of a couple of values. We have overall discontentment, right? Overall discontentment. And each value for each motive, there's a weighting for it, okay, as an example. We can call that, you know, the level of desire or intensity, if you will. So if you go back up to the top, and if we look at some of that naming, right, naming convention as an example, which is right here, the level of insistence. We want to reduce the level of insistence, right? Or, you know, because as that level goes down, right, our discontentment overall for the character is going to go down, for the autonomous character, right? And we always want to try and reduce the overall discontentment in goal-oriented behavior systems, all right? And then there's a couple ways to do that. One thing is that we can also apply time, like we said, as well as, so time issues, so how long it takes, or as well as how convenient something is. So is it difficult? You know, and we could also rate it on difficulty. If, for example, the AI knows that for foraging, time-wise, it's going to take some value, an hour, foraging for food, berries, as an example, in the forest. Maybe it'll take an hour to do that, but difficulty level is easy. It's easy to forage for berries. Berries aren't going to fight you, you know, as an example. That might be one option. But if instead of foraging for berries, I'm hunting for deer, as an example, well, hunting for deer, the deer is going to run away, right? There's going to be more challenge in hunting for a deer than foraging for berries, right? So the convenience of hunting for deer will be lower, right, than for berries. It will be a high convenient item, berries, right? However, we also have to consider that that when it comes to hunting for deer might also take a while because you have to use several skills. Stealth, you can consider, do you have a good stealth skill? Do you have a good hunting skill? Foraging doesn't take much, right? I mean, you pick a berry off of guys, please forgive me, I'm generalizing, right? So again, Samuel says, is discontentment and insistence the terms used often or just named that way for comprehension? It's the most common ways of thinking about it. Discontentment and insistence. Again, from a scholarly perspective. All right. That's good. I'm glad, Neil. So Neil says he's been working on similar things before school. So again, it's the idea behind it, right? That what we're trying to do is give you some ideas about how to, proceed when it comes to using kind of AI systems or AI agents. So let's keep going back with that deer and foraging thing. So I'm foraging or hunting, right? Okay, so then there's convenience, right? And we also have to think about other things like we saw later on, right? We didn't just think about convenience, but we also had this idea of the Smelly goal-oriented behavior. So the idea that something that is, a high complexity, as an example, might be less convenient. Something that takes longer, from a timeline perspective, is less convenient, and you could calculate those things. So let's say, for example, okay, I want to add some of these factors into my to fulfilling my motivations, whatever those motives are. Okay, I have intensity, some kind of, you can call it intensity or insistence, right? I have my overall discontentment that I got to worry about for my character, right? That's going to, basically create realistic actions, okay, as an example. And, I got to think about what's the most convenient goal to go for right away, right? And what's the most challenging goal, okay? And sometimes the most convenient goal is also the most insistent goal. Good example of this. I have, let's say again, I'm making an autonomous agent. One of my goals is eat. I have hunger as an insistence, okay? But I also have another goal, which is goes against the hunger or eating, which is self-preservation, right? And I have an enemy nearby. We can always make it that self-preservation is much higher than eating, right? I mean, you're not going to eat if an enemy's nearby, which we kind of saw in a couple slides before, right? So let's go back to that now, right? So now there's an enemy nearby. What level am I? Okay, do I see a big enemy or a small enemy? How convenient is it for me to be able to fight that enemy and get him off me, so I can go back to foraging for food or hunting for deer, right? What is, I want to get rid of this thing. I want to reduce my discontentment, because right now I'm very discontent. I'm very discontent, and I'm upset because I'm thinking about myself as an AI. I'm really upset because I have a threat next to me, and that threat has to be taken care of, because I'm at the point now where I'm truly discontent. But what if that threat's not really a threat? Example, maybe I have a lower level character, lower level player, a player that doesn't have a lot of weapons. Their overall damage rating is low. They've just started the game. And I'm an upper level enemy. So I have good defenses. Chances are the player's not going to do too much damage to me anyway. It's going to be more of an inconvenience than actually a threat. Okay? So you can categorize, things like that for the enemy, so that maybe even if the player's around, the enemy's still going to forage for food because they're not afraid of the player, right? They're not afraid of the player because the player's not a threat. Okay? Later on, when the player goes up a level, let's say, or they have better armor and weapons, and maybe they have better skills so that they can hit easier, as an example, and maybe regenerate hit point, maybe have a larger hit point base or whatever, the player will be a threat to lower level enemies like that. And maybe what's going to happen is they're going to say, wait, I have a threat. I have to take care of the threat some way. One way to mitigate the threat is leave. Get out of there. Get out of Dodge, right? The other one is fight the player. Challenge them for territory, because you want to be able to eat. That is your motivation, as an example. So it really depends on how you set up these systems and the values that you assign to all this kind of stuff, which is very interesting. You got to figure out how organic this thing could become. But also, one goal could fight the other goal. So I'm fighting the player, but my health, the amount of eating has to go high. Goes to a high level of discontentment after I'm done fighting the player. Or maybe there's going to be another value, like healing is more intense. I have to make sure I regenerate before I eat, or even sleep. So these are the things that we can go. We can also have energy levels where, my energy goes low. If my energy goes low enough, maybe it's a robot character that you have, I need to recharge, right? If I don't recharge, I'm going to stop working, right? So there's the eating idea again. right? So if I stop working, then I'm not functional, I'm dead, right? Until I get recharged again, right? All right, so these are the things that we talked about. How about rule-based systems? One thing is that they're inefficient and difficult to implement versus decision trees or state machines. That's for sure, 100%, right? It's useful when an AI has to reason about the world in ways a decision tree can't do. Okay, decision tree is very cut and dry. If I see the player, then do this. If I see food, then pick it from the tree. Go do these actions or whatever it is, right? So we can use couple common pieces of structure. One is a database containing the available knowledge, right? And the other thing is a set of if-then rules. All right, so the rules can examine the database to see if their if condition is met, and if it is, it may be selected, as an example, and to trigger, right? And then it's whatever the result is executed. All right, so we kind of take our rules and we kind of compare it against database information, and then we can create a decision from there. How does this look? It looks kind of like this. So we have a bunch of rules. If my ammo is less than 10, then if I'm healthy, then, and then some kind of arbiter, and then there's the database. So example would be ammo is equal to 4, right? If ammo is less than 10, right? And if healthy, right? Then if the enemy is sighted, then this is part of our database. These are all the conditions, if you will. So the third component is this arbiter, and it used to determine which triggered rules get to fire from the database. Okay, so it's kind of tricky. So the way this looks is this. So this idea of a condition action rule, right? It causes a autonomous character to carry out an action based on finding a match in the database. So this is kind of interesting. Good thing about the database is it can be quick to search through it. Much quicker than searching through, let's say, as quick as searching through a collection, all right? But the great thing about a database, it could be something that is online and shared, right? And we have a database of actions. We match our condition. We look for a condition in the database. When we search for that condition and we find there's a key value pair, the condition is the key and the value is the action, okay, that we want to take, which is kind of very straightforward. Actions can still fail, right? All that will happen is to only update the database if the actions succeed, which is kind of interesting. So here's an example. My captain's health is 51, Johnson's health is 38, Saleh's health is 42, and Whisker's health is 15, right? As an example, the radio is held by Whisker. Here is an example of a set of states based on health. Whisker's health is less than 15, and the radio is held by Whisker. All right, so this is the condition. Okay, less than 15. If Whisker's health goes lower than 15 and the radio is held by Whisker, then if Whisker's health is 0 and radio is held by Whisker, then Saleh is going to pick up the radio. Okay. So this is kind of the stuff that you would do. You would have a set of conditions and you match them according to the actions, the then. So here's the if and here's the then. So rules that we're going to follow. If this, then do that. If this, then this is going to be triggered. I'm going to trigger some other action or some other behavior as an example. And it's not going to be around goals. It's going to be around another way of generating behavior. Now we can mix and match these things. It doesn't mean that we can't have goals and rule-based systems at the same time, but sometimes one thing can work against the other thing. So we want to make the rule incorporated into the database itself. We add a rule shown at the bottom of the slide, all right, that governs what happens when a certain condition is met. Okay, so here's something. Here's our condition right now. This is our state. 500 kilograms of fuel remaining. 100 kilometers from base. Enemy sighted. Enemy 42. Enemy 21. Currently in patrolling mode. These are all states that we're in. Okay, here's the condition. If the number of enemies cited are greater than 0, check mark. We have 2 cited enemies. And currently patrolling, check mark. Those 2 conditions are met, right? Then remove currently patrolling and add attack first cited enemy. Okay, so that can be something that is a rule. Okay? If then, rule-based system. We also have something called, there's 2 kinds of chaining, forward chaining and backwards chaining. Okay, so again, this is more challenging and more complex. So again, when we start thinking about forward chaining, it starts with the database information and repeatedly applies rules that change the database. So we update the database of information based on the rules. And this is more commonly used, this kind of idea, where the database that gets updated, right, as an example, is something that's new knowledge that's been added to the database. A good example of adding knowledge to the database is there's an alarm condition. The alarm condition persists. I don't have to set up, this is the great thing about a database, I don't have to set up things like Booleans or anything like that. Is there alarm condition? The alarm condition is there. It's there. It's an alarm condition, right? And I can look inside the database if the alarm condition exists. If it does, then do this. If it doesn't, then don't do it, right? So the database is almost like a collection of objects, if you will. And the collection of objects can be represented in different ways. We can represent a collection of objects as a set of documents, right? For example, and the database, by the way, could be just a collection, like a list or an array. That could be my database, right? It could be a real-time database that's live, that's local to my character. Or it could be an online database where it's available, where I can modify my database remotely. So all AIs will follow the same rules as an example. Okay. But forward chaining definitely uses a database and it updates the database as it goes, almost like updating knowledge, world knowledge. Okay. Backwards chaining starts with a piece of data that could be considered a goal. And then the system then works out a series of rule firings that would lead to the current database contents to the goal. And it looks at the then contents to see if it could generate the goal. So it's the opposite way around. So it kind of looks at the, is it possible that I can kind of create this goal, yes or no? If it's not, then it goes to the next one. And it's less common, this kind of idea. Each piece of data in the database could have an identifier and a value. And so a good example of this is fuel is equal to 1,500 kilograms. Where am I? I'm in the patrol zone, right? And we can use the word datum to represent one item in the database. So example, this datum, fuel, has a value of 1,500 kilograms, okay, datum, okay? Each datum, for every datum in data, sorry, say it that way, but that's kind of the easiest way to think about it. For every datum in data. All right. And symbolically, datum will be presented as some kind of an identifier and then the content, where the content is either a value or a list of datum objects. So it could be another set of datum objects. Okay, so here's a good example. The database from the second example might look like this. Captain's weapon is a rifle, right? Captain's weapon is the identifier. Content is a rifle. Rifle is an identifier. Content is ammo. Ammo is an identifier. Content is 36. You see how that works? So that way, each identifier, each piece of datum could have other pieces of datum inside of it to make it a much more complex system. Okay? Johnson's weapon is a machine gun, right? He has ammo of 229. Again, looking at this whole thing, Johnson's weapon, that's identifier. Content is the machine gun. Machine gun is the identifier. Content is the ammo. Ammo is the identifier. Content is 229. Okay? So that's how it can look, almost like nested datum, I think is the right way to say it. So each datum object consists of other datum, which of course is composition, right? Which is what it is. And we can illustrate this in a hierarchy. So like we talked about before. All right. So here's an example. I have my captain, right? He has a weapon. His weapon is of type rifle. The rifle has 2 pieces of datum, ammo and clips. Ammo has 36 as an example of a value, and clips have 2. Okay, so that is 1 piece of datum. The second piece of datum that belongs to the captain is health. The third piece of datum that belongs to the captain is position. Position looks like a transform of X, Y, and Z. Okay, that's the value. So that is the idea of how to create a hierarchy, a datum hierarchy for an object. And each of these things describes state, really, at the end of the day, right? Once I start describing state, when I look at things like, that of the objects in database, once I can encode, remember, when I add things to a database or to a file, what I'm really doing is serializing and deserializing. I want to serialize or encode data so it means something to your program, your game engine. When I serialize it or encode it, I can save it, store it, whatever you want to call it, in a persistent store, data store, like, for example, a collection, a list, array, a queue, stack, whatever. Or it could be something that's online, more persistent, some kind of database, some kind of player preferences, that's local to the machine, other places where I can store my data. I can store it as a file, whatever. That also can be a database, right? And then what I'm doing is, after I serialize it, so I encode it in a certain way, so it looks maybe something like this, I need to, when I bring it back into the system, I need to decode it somehow. I need to be able to read the data, identify what it is, and how I can apply it to the class that I have in my game engine. Okay, so the idea of serialization and deserialization. Okay, coding and encoding, coding and decoding. All right, so here's an example of an algorithm, right, for rule-based iteration, right? So I have my database. I pass in my database in a set of rules. For every rule in rules, it's a for each loop. I create a set of empty bindings, right? If my rule, the if clause matches my database bindings, then I trigger the action that's related to my rule. Okay, whatever that bindings are, the action that's related to there, I want to take that set of bindings from the database, and I want to apply it to the action that I'm going to take for that particular rule, right? For every single one, I'm going to go through each rule in the database. Okay. So there's a couple of structs that they talk about: a data node with an identifier, and a data group that has that is based on a data node. This notation here is Python-like, which when you put anything in brackets like this, it means extends or derives from data node. So where my struct data group derives from data node, right? It has a children value, right? And my struct datum derives from data node as well. It has a value property. Okay, that's how you'd read this up. Okay, so this is kind of the structure. I'm not going to go through all the pseudocode with you, but it's some good readings for you. You can read through it, right? Remember that class and class not, it derives from match. Whenever you see something in brackets like this for this kind of pseudocode, it means derives from or extends. So that's the upper level class, or the superclass. The superclass would be called match. So therefore, class match, right? There's different kinds of matches. There's a datum match, right? And so on. How about rule arbitration? So some of the ways one rule might be chosen to fire over another, which is what the first applicable rule is, right? I could choose the first applicable one that I hit on the database in a list, right? Or I could choose the least recently used if I want to be more random, right? So I want to say, well, I've done these rules over and over again. I've eaten lately, right? So if I've already eaten and if I've already gone to the bathroom, going back with our previous examples, then maybe I want to try sleeping. This kind of stuff, because that's the third thing that I haven't done yet. I can also use a random rule. I can choose a random rule, which is truly random. It doesn't mean it makes it very, very unpredictable, and sometimes not really right. If the autonomous agent seems very, I would say, erratic, if I always choose a random rule. I might have more specific conditions. So the most specific condition, something that's really, really complex, or some kind of dynamic priority arbitration, which means maybe I'm going to base it on probability, right? So maybe I'm going to say that, what's the probability of me performing this action, right? Based on, looking at all the actions in the database. Again, a very interesting way of performing actions. All right, so how does this apply then to the stuff that you're doing? Well, for your assignment 4, there really is no, we haven't asked you for any kind of goal-oriented behavior or anything like that. In fact, all we've asked you for is some kind of decision-making property. So I'm just going to review before we stop, because this is all I want to talk about today in terms of goal-oriented behavior. There's a lot to consume here in terms of thoughts, right? There's two pieces to this presentation. One piece is the goal-oriented behavior piece, and the other piece is rule-based systems. And I'll tell you that rule-based systems are way harder to implement than goal-oriented behavior in many ways. Although we can use elements of both. Like maybe what I want is, I want to keep a database. I want to modify the database. I want to modify knowledge, for an AI. Maybe I want the AI to learn. And this is something that we're going to see later on this semester. Kind of the second last week of class, when we're talking about machine learning and how we can use reinforcement learning to help train an AI to do certain things. Okay, so that is this. Let's talk about our last point for today. I just want to review the details around assignment 4 one more time. And so that way you have everything you need, because I think some of you either have forgotten or haven't even looked at it. And I'm not trying to say anything negative. It's the wrong thing. It's going to come up in a second. There we go. How about we close the other one down? So again, this is due April 18th by midnight. Again, for this one, you may work in a group of up to 3. One thing to note is that I've made different assignment groups. And if you look at Blackboard here, when it comes to groups, users and groups, right? As an example, if I look at groups, right, there's A2 groups, right, as an example. And some people had confusion around this. There's A2 groups, there's A3 groups, and if I keep going, there's A4 groups. Make sure that you're in the right group for A4. Assignment 4 has its own set of groups that you are required to sign up for again. And again, I've done this so that way I can reduce your discontentment, all right, if you're not happy with the group members that you're working with, right? That's the intention or the motivation from this AI, all right? So otherwise, I've in the past, things that I've learned, right? So reinforcement learning, right? And reward. I've learned that when I made it so that you had to stay in the same group the entire semester, that most people were somewhat discontent to very discontent, because they found that they didn't like to work with the same partner for the whole time. And part of that is because group work is challenging, because everyone has different priorities, motives. Okay, so that is why we've done this. So please make sure, if you haven't had a chance to already, long story short, and all joking aside, that you need to sign up for assignment group 4, because otherwise you won't be able to see the assignment or do it. Okay. again, one thing to note is that your assignment 3 must be functional in order for you to, that's the expectation, I think, when it says mandatory prerequisite. If your assignment 3 is not functional, make it functional, guys, before you do it. Even if you didn't hand it in somehow, like your group decided, I can't do it, or you couldn't figure it out, or whatever. Get help with this, right? Because you can't do assignment 4 without assignment 3. And assignment 4 is worth more than assignment 3, right? So that would be terrible if you couldn't. One thing to note is we talk about AI actions, but we never talked about here how things should be done. I didn't say, for example, I want you to create some kind of structure, to do the action. I said, look, you need to have all these AI actions. You must have a patrol action, a move to player action. We've talked about how to implement this, some of this last week with a state machine or a decision tree, but you need to have these actions and they need to be mapped out in code. All right, so close combat action, flee, move to line of sight, move to range, move behind cover, wait behind cover, or range attack. Those are the different kinds of actions we've asked for. All right. Also, there's 2 loadouts, just to reiterate, 2 loadouts. Okay, and if I was going to, draw the scene again, let's do this really quickly because I think this is an important piece. So let's do it from scratch. So let's say I have my whiteboard and I have my game, right? So here's my game with my game screen, my scene. And I have, remember what my player looks like. Let's suppose here's my player, right? And my player also has health. Now, some of you elected to do player health in a screen space way. So I never said that you have to have a health bar on top of the player. It didn't have to be here. For example, in the user interface, you may have elected to make a health bar somewhere else. Some people have done this where they had a health bar up here, right? So player health was here. Okay. I've seen that in some of your submissions. Okay. This is something you might have done. Or instead of doing it this way, some people followed what I asked them to do as well. By the way, in no way one is superior to the other one. It's just a matter of what you feel is best, right? Let's suppose I had some kind of health bar here, right, as an example. So here's your player health. And in this section here, right, you decided to make it a green color or a red color or whatever you wanted to do, right? So that way you could show player health this way, okay? That's your health bar. And by the way, one thing that you could have done in your encoding, right, when you're doing stuff, is you could have made a health bar a reusable component. All right, so you could have made this health bar something that could be reused and used on the player as well as enemies. So let's make an enemy. So health bar could be used on both enemy and player. We're going to make 2 loadouts here. So we're going to make the close combat loadout. Oops. So here's your close combat loadout. The close combat loadout is going to be different goals. We'll make them closer to the player. And we'll make the other loadout down here. So 2 loadouts. So one is the close combat, right, loadout. So we'll call them CC. Or I was supposed to say close combat. Maybe we can fix it like this. It'll make it so that you can see the close combat enemy. We'll make it really small, but you can be able to see where that is. There's your close combat enemy, right? And then there's another enemy, which is your range combat. All right, so range combat enemy is over here, right, as an example. And your range combat enemy, your close combat enemy is going to be based on the enemy subclass that we talked about in assignment 3. All right. And like we said, because your assignment 3 also had health bars for everybody, again, it really depends on how you implemented these. This one. If everything has health bars, so maybe I have a health bar for the player, and I have a health bar for each of the enemies, right? I'm going to make instances of each of the health bars if I did things properly. So each enemy and player all have health bars or some kind of health value, right? Again, if the close combat enemy is trying to do a couple things, one thing we said was that if the close combat enemy has line of sight, right? So here's this line of sight, and they're close enough, then they'll do a close combat attack on the player, all right? If the ranged combat enemy has line of sight, right, and they are far enough, they have to kind of look at an optimal range, they're at the optimal range, then they're going to do a ranged combat attack on the player, all right? Those are the two types. My close combat enemy, when it gets hit by the player and goes less than 25 health, leaves, okay? My ranged combat enemy, anytime it gets hurt, it goes behind cover. So there is, let's suppose, cover like this. And let's suppose that, let me not put it there, but let's suppose it's over here. Here's cover. Let's make it bigger so we can make it more realistic. Right, there it is. There's cover. This is an obstacle, which provides cover. And again, I'm mapping this out for you to help you visualize or conceptualize one of the things that we're doing here, because I think one of the best things to figure out a problem, whether it's a physics problem or an AI problem, is draw it out. Here's my obstacle, which provides cover. I have my enemy, which is this guy right here. He is a ranged combat enemy, right? One of his goals is to move behind cover when he gets shot, right? So how does he know how to move behind cover? Well, let's put him back over here for a second, right? We know that there are also a bunch of invisible nodes all over the place, right? And these invisible nodes, let's make them a different color, right? So let's make these nodes blue instead of green this time around. And let's suppose we have patrol nodes, right? So again, we might have patrol nodes, at every corner where the enemy can patrol around the perimeter of the board, right? We're talking about this as the game board or as the game level. So the enemy can patrol around here, right? That's something that they will do, patrol. That's part of what we had in assignment 3 as well. We also might have some kind of nodes, as an example, that are sitting outside of the obstacles, which is something that we talked about as well. And the obstacles are also destructible, which means chances are the obstacles also have some kind of health bar as well. All right, so that's something we can think about, right? It doesn't say you need to obstacle. Yeah, that's true. Sorry about that. You need some kind of obstacle object, but destructible obstacle will be something that can derive from obstacle and maybe has some kind of health bar as well. Maybe the obstacle itself has a health bar, right? And the health bar will appear probably around it or something else. They have to show the that kind of the level of destruction of the obstacle, whether it's diegetic, so it looks like it's destroyed, or non-diegetic, has a health bar. Okay. And then, so what happens is, if I want to move this guy, this enemy AI here, which is a range combat AI, right? If I want to move them, I'm just going to do one of these. I want to move them. I kind of chopped around this obstacle. Hold on a second here. That's what happens when you draw what I drew, right? So let's just get rid of it, just because, I'm a stickler. Who cares? But you get the point. But the idea here is that I just don't want any extra information. There we go. Good enough, I think, is what I want to say. And let's put that enemy a little lower, redraw the point, and go from there. So let's grab this enemy, put them a little lower, and then put back that point. So I want to show you what happens. So let's say, for example, we're in a position where the player has done damage to the enemy. So that's the state that the enemy's in. And one of the things that it says in assignment 4 is, okay, now that you've taken damage, go to a place behind cover. Well, the way we find cover is there's no line of sight for that particular node. Here we have line of sight. So going here would be a bad thing, right? The player can still get to you. Here, here, here. Okay, I'm fine. Any one of these places. So probably something like this. This is what would happen to the enemy. I'm going to kind of put it in place here so you can see it. This is where they would move behind cover to this particular node, right? If they were shot and they took enough damage to do that. Then after a predetermined or random interval, they would move back out of cover. And they wouldn't move here necessarily. They would move to a place that has the first available slot that has line of sight. Remember, what we want to do is we want to generate these line of sight rays, if you will, that come from each of these nodes. So maybe we'll have a line of sight here, that's green. This has line of sight, that's green. This has line of sight, that's green. This one has line of sight, that's green. Even though it's passing through a close combat enemy, who cares? As long as there's no obstacle in place, all these are green. But when it comes to line of sight, guess what? This one is red, right? Because it doesn't have line of sight. This one is red because it doesn't have line of sight, right? With the character. This one is definitely red because it doesn't have line of sight, you know, with the player, and so on. So those are all red. These are green. So when it comes to moving between the cover and out of cover, you want to move to a node that doesn't have line of sight to go behind cover. When you're moving out of cover, you're going to a node that does have line of sight, okay, with the player. And of course, these would change. So example, if the player moves, and these rays, these line of sight rays, would determine that each of these nodes in real time would have line of sight or not. That is one way of doing this thing. It doesn't mean that you have to do it this way. I'm just giving you an example of what you need to do. You need to follow the behavior that's kind of mapped out here. So example, here's the behavior. Call this rule-based behavior. Call it goal-oriented behavior. Call it decision-making behavior. This is the behavior. I didn't map out things like, neither did Alex. We didn't sit down and say, the insistence is very high. Once you see the word insistence or utility or anything like that, you know you're using some kind of goal-oriented or utility-based system. We haven't said that here. We've said that the enemy, close combat enemy, starts in patrol action mode and continues this action until they have detected the player either by line of sight or if the player is within their detection radius. Those are the two conditions, line of sight or detection radius. When the player is detected, we've gone through this last week in lab, when the player is detected somehow, right, we are out of patrol mode, right? We're not in patrol mode anymore. Once the player is detected and they do not have line of sight, so they have radius but no line of sight, then I want to move to line of sight action, like we've talked about before. If the close combat enemy has line of sight, then move to player action. If the close combat enemy has line of sight and is within close combat action, perform the attack action, right? And if the close combat enemy's health drops below 25%, they will perform the flee action, which means to get the hell out of dodge, right? Get out of the scene. And that is one type of loadout. The other type of loadout is more complex because it does that move behind cover and wait behind cover action, right? So that's kind of stuff, something that it does. Destructible environment, basically, it will include a health bar object from assignment 3. So if this happens to be a destructible obstacle, let's make another obstacle that's destructible, and we'll put it up here. You don't have to have them all destructible, remember? You can have some of them destructible and some of them not. And it tells you that. So this is, let's say, a destructible obstacle, right? So let's put that in there. Destructible obstacle, right? Which also can provide cover if we really needed to. Here's a destructible obstacle. And the destructible obstacle is also going to need some kind of health bar. Whether you incorporate it and make it smaller, whatever you do, you need to have it. That's the requirement. So making a health bar class, that's a really good idea, right? Because you need to use it for the destructible object. So when the destructible object takes health, and there's a couple ways to mitigate this, because otherwise the scene can be very cluttered. What you could do is you can make it so that the destructible object only shows the health bar when it's being hit. Same thing with actually any of these things. You might decide, I don't want to show the health bar at all unless the enemy is getting hit, and I want to show it after it gets hit for a certain interval. Like, for example, I want to show it for 1 second, 60 frames, right? After 60 frames, it'll disappear, or I can make it fade out with some kind of lerp effect. I can use lerping, a linear interpolation, and go from fully opaque to fully transparent, right? So it's not showing, right? So that's kind of an effect, a fade out effect, if you will. All right, so again, so some kind of destructible obstacle, and the destructible obstacle will have a health bar. That's what it's basically saying here, okay? And this can be destroyed by taking hits from either the player or an enemy. So it's not going to be, kind of invincible to player attacks. That's for sure, right? Don't forget to remove the obstacle from play when it is destroyed, so it doesn't have to be avoided and enemies cannot use it for cover. And then it says create an appropriate animation and sound effects to play when the destructible object is destroyed. Make half of the objects in the scene destructible. Half. Okay? So one thing we said was, if you go further up, we talked earlier in assignment 3. Let's go back to assignment 3 for a second. We talked about it having a certain number of obstacles, right? So this is the thing that we told you guys to have. Okay, so it says mandatory criteria. Going back to assignment 3, here's the play scene and requirements. You have debug keys, combat capabilities, game status, and obstacles. So your play scene will include at least 4 obstacles, right? At least 4 obstacles. So that means that if I only have 4 obstacles in the scene for assignment 4, that means 2 of them must be destructible, because that's what we said here. We said that at least half of your obstacles have to be destructible. Okay? All right. Yeah, it could be, if, again, you have to have 4 obstacles. You have to have at least, how many enemies are we making? So one thing is, 1 of each is the way to go for sure. That's what Samuel said, and it's correct. At a time, 1 of each. And this is minimal, guys. Like, you may decide to add more than 1, but later on. But remember, what this game is almost like a how long can you survive kind of game, right? For the player. And if I can kill the enemies fast enough before they leave the scene. Okay, so that's something that we want to do. So enemy respawns. If an enemy flees the scene, then a new enemy will respawn, enter the scene, and within a random interval, some kind of time frame. And the new enemy can be of either type. Just because you've lost a close combat enemy doesn't mean you're going to get the same close combat enemy back. The new one that may spawn will be maybe another ranged combat enemy where they keep their distance, right? Or if a ranged combat enemy leaves because they got hit, a new one may come back and it might be a close combat enemy. All right? And this is the win condition. If the player defeats both enemies without either of them fleeing the scene, then you win the game. Display a label somehow on the scene that says you win or something similar, and display some kind of restart button that allows the game to restart. Okay? So that's really the game that you're making. It's a build on everything else you've done for assignment 3. Any questions around assignment 4? Again, this looks like it's not that challenging because we built some of these things out. But believe me, getting these to work properly, the animations and related sound effects to sound right, the timings and all that kind of stuff is where you're going to spend a lot of time. Guys, we're sitting now at the 30th of March, right? Almost the last day, I would say, of March, right? Almost, second last day of March. And this thing is due the 18th. And you're going to say, I have 18 days, 19 days, including tomorrow. I got lots of time. You don't have lots of time. This is a way more difficult part than assignment 3 because you have to actually implement the behavior. There's behavior that needs to be done that's more complex. So again, it really depends on what you want to do, how you want to implement it. Notice that we just said AI actions, right? And here's your, your different enemy loadouts. Just going through it again. Your destructible environment, enemy respawning, winning condition, and that's it. I haven't told you how to do it. I didn't say you must use a state machine. You must use a decision tree or a behavior tree. I didn't say that here at all. However, let's take a look at what assignment 3 says, right? Because assignment 3 also has requirements that have to be met in assignment 4, right? So as we scroll down, it says that you have an actor sprite, a collection of nodes that are basically just going to be a an invisible position on the screen. We have different kinds of keys. These, by the way, these keys are still going to be there, right? They're still going to work for your game because everything that was in assignment 3 is still available in assignment 4, right? Player animations and player combat abilities and all that stuff is going to be the same. And your base enemy setup, right, as an example, is also going to work because, I mean, obviously you're not going to have a base enemy class anymore. Your base enemy was just to get you going, moving, patrolling, getting that stuff set up, and animations and all those things are ready to set up. Line of sight and detection radius should be already in place where you can attach them to different nodes, and that's it. We haven't said use a state machine, use a decision tree, use a behavior tree. You can use whichever decision type you want or structure for your final game. It doesn't matter as long as it's well implemented. Okay, questions around assignment 4. I went over it again because I wanted you guys to have another look at it before we moved on. And I think it's important because if you look at assignment 4, there's lots of little details. So hopefully whoever you were working with in assignment 3 groups, you'll move again with assignment 4 groups. Make sure you sign up for a group. If you haven't done it, do it today. Don't wait. Okay. Otherwise, that's it for me, guys. If there's no questions, I'm going to see you guys during the first lab, which is coming up, right? And that's coming up at 12, so in about 35 minutes or so. And the second lab is a couple hours or a few hours later at 4 o'clock. Samuel says, I'm kind of curious as to how many people use a tree compared to a state machine. Oh, let's take a poll. Who used, does anyone use a state machine or a tree? So some people are leaving, it's okay. State machine, let's see, check marks for state machine. Take care, Miguel. I'm not getting a lot of takes. Some people are taking off now. I probably should have used this question later or earlier today, right, as opposed to now. Anyways, don't worry about it. Well, maybe we'll do a little poll next time we get together. I'll ask that question for assignment 3 and 4, what you guys are planning to do next week. Guys, thank you so much. Neil did both. That's awesome. A combo, it makes sense, right? It makes sense, Neil. All right, thanks, guys. Take care. I'll see you during lab. So first lab is at 12 o'clock. I'll keep this channel open for us. Take care, Catherine. I'll see you later, right? So we'll keep the Zoom call open, and we'll start it at 12 promptly, the lab. All right? Thank you so much, guys. I'll stop recording now.